The effect of enclosure upon sounds has been known and exploited since antiquity. Enhancing the mystical qualities of worship spaces and music from the caves of the Neanderthals through medieval cathedrals to present-day concert halls. Christchurch Town Hall design and the discovery of the significance of lateral reflected sound on concert hall preference are inseparable. To put this talk in a wider context, I want to start by quoting part of a recent poem about the essential simplicity of the universe. Sublime simplicity. Thought, stuff of singularity. A universe from nothing, seething with everything and still becoming. A universe tuned for life, life tuned for consciousness. Mankind tasked with survival. And now the wonders of mathematics, music, poetry, art, aching to connect with that thought. And after 14,000 million years, consciousness, the crowning glory of evolution. Music is one of the high points in the evolution of consciousness and the human reflective brain, not least because it apparently has no relevance to survival of the species, and yet as a race we devote great resources to making and listening to music. The Philharmonie has cost 660 million euros. It is my hope that the proposal for this talk may show how a weakening of localization may help us to discuss this mysterious phenomenon. In deference to our location, I will start with some recollections about the origins of the town hall design, some seminal moments in the design of this great building and my own part in it. The Christchurch Town Hall, New Zealand, was opened on September the 30th, 1972. It is no exaggeration to say that this design was unique. In 1966, I recall the announcement of an architectural competition for Christchurch Town Hall. Ron Muston was then the chairman of the NZIA. I'd been helping him with the design of the chapel for St. Patrick's College in Wellington. There were few acoustic consultants in New Zealand. Even the term acoustical designer had yet to be heard. Leo Brannick's great work, music, acoustics and architecture, was newly on the shelves, delayed from 1962 by the adverse criticism of the New York Lincoln Center Philharmonic Hall acoustics. After reviewing the 54 most prominent halls worldwide, Brannick had concluded that desired acoustical intimacy was caused by what he defined as the initial time delay gap, ITDG, in milliseconds after the arrival of the direct sound, and that this could account for preferred designs. Brannick's previous books had been a major influence in my honours year in architecture in 1955. 8 years later, I had just received a major research grant from the New Zealand research grant committee and started on my PhD study of acoustical absorption in New Zealand. With this background, I felt confident to comment as required on the shortlisted designs for the town hall at the second stage of the competition. I expected to depend on Baranik's book when I agreed to this commission. In 1967, I started my sabbatical in the UK. It was snowing the day we arrived in Southampton. 2 of my children were running shipboard fevers from measles and mumps, but with the help of Elvin Richards, the head of the new Institute of Sound and Vibration Research, we settled in and I engaged again with my PhD research. It had nothing to do with Christchurch. I had devised an experiment to measure the effect of reverberated noise on the central nervous system. The details are irrelevant here. Mid-May, the 5 shortlisted designs arrived by air from Christchurch with a request for my cabled report within 2 weeks. In the meantime, the Lincoln Center debacle in New York had resulted in a description of the acoustics there as mud mixed with broken glass. Baranik's theory of the ITDG had failed. The prevailing view in the United Kingdom, see the Royal Festival Hall, was based around the idea that somehow a rectangular shape was preferred to produce what the designers designated singing tone, a property conspicuously missing from the finished Royal Festival Hall. No one knew why. As I looked through the 5 shortlisted designs, I realized that there were no rectangular spaces. The failure of Baranik's monumental work meant that there was no way to inspect a drawing and predict a satisfactory acoustical experience. The prediction of reverberation time, after all, has no reference to room shape. My supervisor, Phil Doak, at the ISVR, directed me to recent work at Göttingen on the audibility of reflections of speech. This is Gottlob, Zebrasse, and Borghoff. I translated these papers from the German, and it appeared that there was a masking effect where a strong reflection might obscure weaker reflections. It also struck me that the premium acoustic effects in music rooms might depend on the audibility of lateral reflections. It seems obvious. We hear with 2 ears. Frontal overstage reflectors, as in the Royal Festival Hall, are ideally placed to produce masking of weaker lateral reflections. I analyzed this idea for 2 contrasting shoebox shapes for concert halls and wrote it up. Doak said I should send my paper to Göttingen, and I did. To my surprise, I received a reply by return from Professor Erwin Meyer, the grand old man of European acoustics himself, inviting me to come over to discuss this fresh idea. The rest, as they say, is history. The theme of my thesis changed with this insight. Instead of treating reverberation and reflections as a negative, I came to see them as a positive aspect of sound in rooms. Here are two of the original competition drawings. It was obvious to me that while the architectural idea was clear and masterfully worked out, the architects had no idea about how sound behaved in such spaces. See the proposed ray diagram. With these insights, I wrote up my review of the designs and sent it off to New Zealand. Miles Warren came to London as soon as the winner was decided for workshops with engineering design consultants and me, and discussion on this new idea about lateral reflected sound in music spaces. By a beautiful coincidence, on successive nights, Haydn's Creation Oratorio was being performed in the Royal Festival Hall, and then the next night in the Concertgebouw in Amsterdam. The Royal Festival Hall was almost devoid of audible lateral reflected sound. The Concertgebouw was rich with it. Miles was convinced, a wholly successful demonstration of the reason for my recommendation. Miles went on to the Berlin Philharmonic, where there are seats with and without significant lateral sound, while I returned to Göttingen. Here is a schematic of the reflector system derived from the London workshops with EDC and Bill Allen and myself. Next slides show the first model of the town hall, made by the lab workshop at Göttingen to demonstrate for me the pitfalls of elliptical rooms, as if I didn't already know that. Dieter Gottlob, who became a close friend, explained their equipment setup. R.I.P. Dieter. It was the start of several years of collaboration with the Göttingen laboratory. The developed design over the next 3 years was interspersed with research. The next slides detail a few high points in this process. I needed a scale model in which to measure the reflections. The technology, as you've seen in the previous slide, was available at Göttingen and also in the Munich Technical University. It was not cheap. Professor Spandeck offered to do a 1:25 scale model for 1% of the building cost. Impossible in the budget for the town hall. In typical New Zealand pragmatism, Warren and Marnie themselves made a 1:48 model. That is, of course, a 1/4 inch equals a foot, close to 1:50, and shipped it to me in WA. I suggested the completion of the sidewall reflectors in the halo of upper surfaces and sent the coordinates of all the corners numerically to Christchurch. I also realized that plane reflectors proposed from the workshop in London would provide frontal reflections for radial seats below them. This led me to propose a change to dihedral surfaces, which would solve this problem. A simulation of the lateral reflection improvement in the lab convinced the architects to make this rather radical change. Following the completion of my PhD in Southampton, I had started a new position in the fledgling School of Architecture in Perth, Western Australia, with a rather generous establishment grant for my laboratory. I had also accepted a watching brief from the architects for Christchurch, but the principal acoustical consultants were still Engineering Design Consultants London. The partner involved was reluctant to travel, and after some 6 months, Warren and Marnie asked me to become involved again. Research proceeded at my new laboratory, and shortly afterwards, Mike Barron, who had started his PhD on this project in Southampton when I graduated, came out to complete his PhD with me. He was directed by Doak to challenge my hypothesis, but finished up by endorsing it. Meantime, Ada had progressed with his program as described in slide 17. The output of Ada's work was graphical. This is a plan of the stalls showing source position and seat positions requiring correction. With the computer power at everyone's fingertips these days, we forget what a feat this was in 1970. The program was run on a PDP-6 ex-NASA computer that occupied several rooms and took all night to run for a single source position. It was certainly the first such application in our hemisphere and possibly in the world. T.B. Ada deserves special mention for his groundbreaking work. Echoes were located and treated. The slide shows a plot of stall seats deficient in early lateral energy, and the system was interactive. The echogram at the selected seat, shown with a cross, could be inspected at will. As the slide illustrates, the town hall was the first design in the world to have the audibility of lateral reflected sound predicted by computer. More detail will be found in the book, A Dream Renewed, edited by Ian Lockhead. To complete his PhD thesis, Mike devised the equipment to measure the reflected lateral fraction in such spaces as the town hall, and he measured them in it prior to the opening. In the town hall, we had one hard hat concert, and 2 days later, the opening notes of the Ritchie fanfare. History shows how seminal Barron's PhD was in identifying the role lateral reflected sound plays in the design of rooms for music. There are several points in the summary slide that require comment. Is there an upper limit to the lateral fraction? A reflection too early or too strong will cause an image shift. The spatial impression produced by a lateral reflection at 40 degrees is independent of its delay even after it is audible as an echo. A brief word about ensemble. As a singer, I was keenly aware of the need for reverberation for singers to make an ensemble. That was fulfilled in the design. In the first music, however, there was difficulty on stage for instrumentalists to play in ensemble. The overstage reflector, omitted because of cost by the architects and without reference to me, led to a further sabbatical in Göttingen, which established the need and desired bandwidth of instrumental reflections. By the time this groundbreaking work was published, my reflector design was in place and the ensemble difficulty had disappeared. The following decades of research around this topic resulted in alternative definitions. Interaural cross-correlation as a measure of envelopment by Schroeder, Gottlob and Zebrassi. Late lateral sound as a reverberant component, LEV, by Bradley and Sulodra, and improved measuring techniques, including the next slide. MDA developed the iris prot to capture graphically the distribution in time and direction of reflections. Now, some 50 years later, I have pondered the topic of this paper and the role that localization plays in the importance of lateral reflections. We start then by recalling some of the literature concerning this human capacity to identify and locate acoustic sources. The evolutionary imperative to localize sources is there from the start, either as predator or prey, or, as the slide indicates, the opportunity to discuss localization. Localization is most accurate in anechoic conditions or given low noise outside, precision of about 4 degrees depending on the source and in quiet conditions. Inside a building, reflections of sound from the room surfaces or objects within it complicate hearing. Human hearing integrates reflections of speech out to about 50 milliseconds after the arrival of the direct sound, increasing loudness and clarity. Speech is relatively uniform as a source, and it's easy to design surfaces to exploit this capability and to suppress later reflections or reverberant energy. Music is much more variable, some akin to speech, others very different due to its wide range of sources and musical styles. In fact, there was a succession of silver bullets proposed during the preceding 50 years of research into the source of excellence on concert hall sound. Examples are diffusion, the rectangular plan I've already mentioned, Brannick's IDDG, and overstage reflectors like the Royal Festival Hall. My suggestion of lateral reflections was another, given substance in numerous experiments in the United Kingdom, Japan, New Zealand, Germany, France, and North America. But the quality of the listening in a concert hall is certainly multi-dimensional, and I want to elaborate this fact. There is no silver bullet, but there are two pathways by which an acoustic signal reaches consciousness. First of all, the binaural lemniscal neurophysiological pathway. This is, in effect, the wiring of the brain. These start at the organ of Corti in the cochlea on either side and relay in the cochlear nucleus. There they bifurcate and transmit to the superior olive on both sides. These bodies are the primary site of the comparator on which the measurements of interoral level and time difference depend. After several further relays in the brainstem, they terminate at the primary auditory cortex as indicated in the diagram. On the way, of course, the cochlea performs a first frequency analysis. The non-lemniscal cognitive pathway. This slide lists the non-lemniscal pathway in parallel with the neural pathways. One sees readily that these, while originating in the binaural pathways, are whole brain functions. They give meaning to acoustic inputs in language, comprehension of prose or poetry, and in music, emotional impact, interpretation, and the details of tuning. Detailed studies of the astonishing signal process ability of the brain to separate competing acoustic streams by David Griesinger and others adds a further dimension to the whole brain function. And now I will elaborate on the last two items on the list. The objective of a performance must be to produce a gestalt that encompasses the music and the composer's intention, the architecture, presence, and the background cultural norms which govern the performance occasion. Gestalt lacks an English equivalent. It's often translated as form or design, but it means a totality greater than the sum of its parts. It refers to the more that, say, a painting is than its colors or brush techniques. I propose it here to mean the more that a concert experience is than technical ability, on-stage conditions, the architecture, audience comfort, and the value of any of the acoustical metrics we use. Listeners are present in a concert to engage with the music as conceived by the composer and via the musical skills of the performers. The room must contribute to this engagement as one of the dimensions of Gestalt. There is also prejudicial cultural inertia. Prejudice regarding, say, diffusion, colour, room shape, visual impression, and the like may inhibit objective thought about the sound. It is unlikely the Christchurch Town Hall could have been built in Europe during the 60s. Such prejudice links with the search for silver bullets, as mentioned earlier, myths about diffusion, colour, etc. persist even today. Later, I reflected that the principal acoustic feature of sound in rooms is a weakening of localization of the source, sometimes enhancing the acoustical impression and sometimes interfering with the communication between source and receiver. Only in a few rooms does this occur for music, while cherishing the speech clarity humans depend on to communicate verbally. This town hall was the first of its size, which showed the possibility of truly multi-purpose rooms. The distinctive form of this room and its reflectors was intended to provide every listener with unmasked lateral reflections, while measuring the reverberation time with a 45mm pistol. I needed to warn the audience to cover their ears. In an RT of about 2.2 seconds, speech clarity should have been impossible, but I found I could address an audience in excess of 2,000 unamplified. This phenomenon was remarked by Ben Terfel at a concert shortly before the 2011 earthquakes. Dr. George Dodd, my long-time associate, pointed out in 1973 that the form of this room separated the early directed reflections laterally from the reverberant field. The next example is the Philharmonie de Paris, which we completed in 2015. As I flew to Paris for a design workshop with architect Jean Nouvel, I studied the program Acoustic prepared for the competition committee by their advisors Carla and his colleague Denaru. This was simply the most detailed acoustic brief I had ever seen. As I read it, I realized that it might as well have been a description of the Christchurch Town Hall acoustics. I vividly recall the moment after lunch in a hotel in Biarritz when the PDP design crystallized. The large upper space I had envisaged queuing from Christchurch had just been shown to be prohibited by town planning height ordinances. I sketched an alternative, distributing the additional volume and providing a bicameral concert hall. Its volume, though I did not know it at the time, turned out to be 70% larger than most concert halls of this capacity. Jean Nouvel had just asked me, "But Harold, will it work?" The design competition render, which follows, shows how seminal this sketch was in sympathetic architectural hands. The Christchurch Town Hall experience over 50 years gave me the confidence to say yes. The bicameral design allows the control of the early integrable direct and reflected acoustic energy, independent of the reverberant field, just like Christchurch. Diffusion is achieved by convex curvature of the reflecting surfaces and introduced surface roughness where needed. In PDP, there is indeed an architectural ensemble and presence which supports the musical gestalt. This was summarized by Sir Simon Rattle when he wrote about his experience there with the Berlin Philharmonic Orchestra in one of the first concert seasons in 2015. It occurred to me that I was listening to one of the great acoustics in the world. Lucky Paris. It started here.